Welcome to AI Frontiers, where we explore the cutting edge of artificial intelligence research. Today we're diving into the fascinating world of computer science robotics through 28 groundbreaking papers from August 28, 2025. These papers are reshaping the very foundation of how robots think, learn, and interact with our world, representing more than just academic achievements. They're glimpses into a future where robots don't just follow programmed instructions, but truly understand and adapt to the complex, unpredictable world around us. Picture this: a robot learning to play table tennis so well it can rally 106 consecutive shots with a human opponent. Imagine a machine that can understand your casual instruction to carefully place that fragile vase on the highest shelf and execute it flawlessly. What if I told you that these aren't science fiction scenarios but real achievements happening right now in robotics labs around the world? These remarkable demonstrations represent the boundary between programmed and intelligent machines dissolving before our eyes. Robots are now thinking, adapting, and collaborating like never before, moving far beyond their traditional role as mere automated tools. We're witnessing a robotics renaissance, where traditional approaches are being revolutionized by the integration of artificial intelligence, mechanical engineering, and human-computer interaction. Unlike the isolated industrial robots of the past, today's intelligent machines must operate in the messy, unpredictable real world, where conditions change rapidly, humans behave unpredictably, and success often depends on split-second decision-making. These 28 papers reveal glimpses of truly adaptive machines that can perceive their environment, make decisions under uncertainty, and learn from experience. The convergence of massive computational power, revolutionary advances in machine learning, sophisticated sensor technologies, and growing automation needs is creating unprecedented opportunities for breakthrough discoveries. Think of computer science robotics as the brain of the robot revolution. If traditional robotics is like building a sophisticated mechanical body, then computer science robotics is about creating the intelligent mind that brings that body to life. It's the difference between a puppet and a thinking, reasoning entity that can perceive its environment, make decisions under uncertainty, and learn from experience. This field encompasses everything from mathematical algorithms that help robots navigate through crowded spaces to artificial intelligence systems that enable them to understand natural language and collaborate seamlessly with humans. What makes this field particularly exciting is its interdisciplinary nature, much like a master chef combining ingredients from different cuisines to create something entirely new. The first major research theme emerging from these papers is embodied intelligence and world modeling, representing a fundamental shift in how we think about robot intelligence. Instead of treating perception, planning, and control as separate modules like a traditional assembly line, researchers are developing integrated systems that understand the world through physical interaction. It's like the difference between reading about swimming and actually jumping into the water. Robots are learning to understand their environment by actively engaging with it through short-horizon interactions that capture the essence of physical manipulation. This approach moves beyond pure observation to enable genuine understanding through tactile experience, where robots learn what simulation simply cannot teach about the physical properties of objects and materials. The second major theme focuses on human-robot collaboration and safety, addressing the paramount need for safe and effective interaction as robots increasingly share our workspaces. This goes far beyond simple collision avoidance to encompass predictive understanding of human behavior, adaptive safety margins based on uncertainty, and natural interaction modalities. Think of it like learning to dance with a partner. The robot must not only avoid stepping on your toes, but anticipate your movements, adapt to your style, and create a harmonious interaction that feels natural and fluid. Advanced safety frameworks now balance caution with efficiency, enabling robots to work more aggressively when human behavior is predictable, while automatically increasing safety margins when uncertainty is high. This represents a sophisticated understanding of human intentions and the development of truly collaborative partnerships. Learning-based control and adaptation represents our third theme, marking a dramatic departure from traditional robotics approaches. Instead of requiring precise mathematical descriptions of every possible scenario, modern robots embrace learning-based approaches that can adapt to changing conditions and improve through experience. It's like the evolution from following a rigid recipe to becoming an intuitive cook who could adjust ingredients based on taste, available supplies, and the preferences of dinner guests. These systems handle uncertainty and variability in dynamic environments through real-time adjustment based on sensory feedback, enabling robots to operate effectively even when conditions deviate significantly from their training experiences. This adaptability is crucial for deployment in real-world scenarios where perfect predictability is impossible. One of the most significant breakthroughs emerging from this research concerns the scalability of embodied learning, addressing a fundamental challenge that has long plagued the field. Researchers have discovered that by restricting learning to short-horizon primitive actions, robots can achieve dramatically more efficient learning while maintaining the ability to compose these primitives into complex behaviors. It's like learning to write by first mastering individual letters and basic strokes, then combining them into words, sentences, and eventually complex literature. This finding suggests we may be approaching a GPT moment for robotics, where pre-trained models of basic physical interactions could serve as the foundation for a wide range of robotic applications. Just as large language models learn general patterns that transfer across many language tasks, primitive embodied world models could capture general patterns of physical interaction that transfer across countless manipulation tasks, potentially revolutionizing how we develop and deploy robotic systems. Today's featured paper, Embodied World Vision by Qwen and colleagues, represents what may be the most significant step toward general-purpose robotic intelligence we've seen in recent years. This groundbreaking work tackles the fundamental challenge of creating systems that can seamlessly integrate multimodal reasoning with physical interaction across diverse tasks and robot platforms. The researchers developed a unified vision text-action architecture that processes images, text, video, and action sequences as parts of a single coherent system. Rather than using separate encoders for different types of input, it employs a unified transformer architecture that treats all inputs as sequences of tokens, enabling the discovery and leverage of complex relationships between what the robot sees, what it's told to do, and how it should act. This represents a revolutionary step toward general-purpose robotic intelligence that mirrors human flexibility and adaptability. The technical innovation behind Embodied World Vision lies in its unified transformer architecture that treats images, text, and actions as token sequences within a shared latent space. This design enables sophisticated cross-modal reasoning, where visual observations, textual descriptions, and robotic actions are embedded together, allowing the model to learn rich representations that capture the relationships between perception, language, and action. The training methodology combines autoregressive decoding for generating coherent action sequences with flow-matching denoising for iterative refinement, similar to how large language models generate text, but adapted for physical control. Perhaps most remarkably, the system demonstrates cross-embodiment generalization to robot platforms. It has never seen during training, successfully adapting learned behaviors to account for different kinematic structures and actuator capabilities. It's like watching a pianist sit down at an unfamiliar piano and still play beautiful music. The real-world impact of embodied World Vision is demonstrated through its ability to understand nuanced instructions with context and safety considerations. When instructed to carefully place the fragile vase on the highest shelf while avoiding obstacles, the model demonstrates understanding of multiple complex concepts simultaneously: object fragility, requiring gentle handling, spatial relationships for identifying target locations, and collision avoidance for path planning. The system maintains coherent behavior over extended multi-step tasks, successfully handling kitchen cleanup demonstrations, where it identifies dirty dishes, determines appropriate cleaning procedures, and organizes items in their proper locations while adapting to unexpected obstacles and changing conditions. This performance suggests the model has developed something akin to a general understanding of manipulation that transcends simple memorization, representing abstract manipulation principles that can be applied across diverse scenarios. Looking toward the future, this research opens exciting possibilities that stretch our imagination toward a world where robots could serve as truly general-purpose assistants. We're moving towards systems capable of understanding natural language instructions and executing them across vast ranges of physical tasks, from helping elderly individuals with daily activities to assisting in disaster response scenarios or working alongside humans in creative endeavors, like art installation or architectural construction. The implications extend beyond individual robot capabilities to entire ecosystems of intelligent systems, where collaborative robot networks could share knowledge and coordinate complex multi-agent tasks. Imagine construction sites featuring dozens of robots that communicate about project status, share learned skills, and adapt their roles dynamically as conditions change, or healthcare robots that adapt to individual patient needs and learning styles. These seeds planted by today's research are becoming tomorrow's forest of robotic possibilities. The revolution is here, and these 28 papers demonstrate robots transitioning from programmed tools to intelligent entities, capable of genuine understanding and adaptation. The convergence of embodied learning approaches, sophisticated human collaboration frameworks, and unified architectures like Embodied World Vision is leading this transformation toward general-purpose robotic intelligence. We've seen how short-horizon primitive learning enables scalable skill acquisition, how uncertainty-aware control synthesis balances safety with efficiency, and how unified multimodal architectures can achieve remarkable cross-task and cross-embodiment generalization. However, as these technical advances accelerate, we must carefully consider their ethical and societal implications, ensuring that the development of increasingly capable robotic systems serves humanity's best interests, while addressing questions about employment, privacy, safety, and the appropriate boundaries between human and machine capabilities. This analysis was created through AI synthesis using Claude Sonnet 4 from Anthropic for comprehensive paper analysis and interpretation. Text-to-speech synthesis is powered by Deepgram technology to ensure natural, clear audio delivery. Image generation is enhanced by OpenAI systems to provide visual context and engagement. Qwen expert review ensures accuracy and proper contextualization of complex technical concepts. All original paper references are provided for verification and further reading. This multi-layered approach combines artificial intelligence capabilities with human oversight to deliver accurate, accessible, and engaging content that bridges the gap between cutting-edge research and public understanding. Subscribe to AI Frontiers for daily breakthroughs in artificial intelligence research. We provide deep dives into cutting-edge papers and trends, expert analysis of robotics, machine learning, and emerging technologies, connecting you with a community of AI enthusiasts and researchers. Never miss the next breakthrough in artificial intelligence as we continue exploring the frontiers of what's possible. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archivepreprinserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archivepreprinserver.org.